Hello and welcome to the MathOS channel in English. The Rolle'S theorem is a very famous result which can be found in quite every first course in calculus. This theorem is named after Michel Rolle's, who was a French mathematician living between the middle of the 17th century and the beginning of the 18th. Rolle's devised a new method for the computation of the roots of algebraic equations. This method, known as la méthode des cascades, is, in a way, the ancestor of the following theorem. For any continuous function f, defined on a closed and bounded interval ab, if f is differentiable on the open interval, and if it attains equal values at a and b, then there exists some real number c, strictly comprised between those bounds, such that the derivative of f vanishes at c. This result was in fact discovered short after 1820 by the French mathematician Cauchy, and was finally named Rolle's theorem even later by others. Geometrically speaking, it means that somewhere on the graph of f you will find a point at which the tangent line is horizontal. We should notice that the number c has no reason to be unique. Two or more numbers may satisfy this property. There can even exist infinitely many such values, as we can suspect by looking at this picture. In this video, I'd like to talk about an extension of Rolle's theorem where the closed and bounded interval ab will be replaced by some closed and unbounded interval like those ones, or even the whole real line. With no loss of generality, we can restrict ourselves to the first type of interval because the two others can be treated in a quite similar way. So, we assume that f is a function, defined and continuous on some closed and unbounded interval from a to infinity, that f is also differentiable on the open interval, and that its limit as x approaches infinity is f of a. And what we want to do is to prove that there exists some real number c greater than a such that f prime of c is 0. I'd like to show you two distinct proofs. Each one will essentially rely on the classical version of Rolle's theorem, but in a slightly different way. Okay, let's start with the first proof. The idea behind it is merely a change of variable. We are going, so to speak, to shrink the unbounded interval from a to infinity and reduce it to some bounded range. For that purpose, consider the function phi defined on the right open interval 0, 1 by this formula, and define an auxiliary function g, which is the composition of f and phi. We notice that the limit as t approaches one from the left of g of t is equal to the limit as x goes to infinity of f of x, which is f of a, and this is equal to g of 0. And this enables us to consider the continuous extension of g, denoted by uppercase G, which is defined by this formula. Now, we can apply the classical Rolle's theorem to uppercase G, and we know that there exists some d between 0 and 1 such that uppercase G prime of d is 0, which means the following relation. But this fraction is not 0, and so we have reached the desired conclusion. F prime vanishes somewhere inside its domain. In short, the previous change of variable has made the job. Our original function, which was defined on some closed and unbounded interval, has been replaced by another one defined on the bounded right open interval 0, 1, which in turn was extended to a closed unbounded interval AB. And then the classical Rolle'S theorem has been applied to that very last function, providing the solution to our problem. Now let's go for the second proof, which, in my humble opinion, is a nice proof by contradiction. If we could be sure that there are distinct real numbers u and v, both greater than a, such that f of u equals f of v, then we could conclude by applying Rolle's theorem to the restriction of f to the closed and bounded interval uv. Suppose there is no such pair. This assumption means that f would be injective, and we know that any continuous and injective function defined on any interval must be strictly monotonic. But this cannot be the case, because if f was increasing, then we would have the following inequality. And if f was decreasing, then we would have the reversed inequality. And we have assumed from the beginning that f of a is equal to the limit of f at infinity. So we are done. And we have reached the desired contradiction. That's it. I hope that you like those proofs. Now it would be interesting to mention at least one or two applications of this result, and I intend to do so in the next video. So stay tuned, and I'll see you very soon on this channel.